Swayam Prabha. Digital India. Educated India.
Now we'll consider a numerical example for the case with 0 input. So this is 0 input. You can imagine that there was a voltage source here which is set to 0, and I'll assume that the capacitor voltage at t equal to 0 is 5 volts. Okay. Now we know that with 0 input, the variables, all the variables in the circuit, and in particular the capacitor voltage follows this. Okay. And the time constant RC for this case is the product of R and C, and let's say R is 2 kilo ohms and C is 1 nanofarad. Then RC is 2 kilo ohms times 1 nanofarad, which is equal to 2 microseconds. Okay. And the initial condition, it's already given to be 5 volts. So the solution to this is 5 volts exponential minus t by tau, which is 2 microseconds. Okay. Now it's also useful to always sketch these to find out how they look like. At t equal to 0, obviously it starts at 5 volts. This is Vc, and it has an exponential shape. Okay, and the slope at t equal to 0 you can find by differentiating this and setting t equal to 0. So the slope at t equal to 0 will turn out to be minus 5 volt by 2 microseconds, or minus 2.5 10 to the 6 volts per second. Now this can also be inferred from the circuit. At t equal to 0, we have 5 volts here and 5 volts there. Okay, they are in parallel. So a current of 2.5 milliamps, which is this 5 volts divided by 2 kilo ohms, will be flowing that way. And we know that the rate of change of capacitor voltage is the current divided by the capacitance. And the current, if you take the signs for Vc this way and by passive sign convention, the capacitor current is minus 2.5 milliamperes and C is 1 nanofarad. Okay, so this will come out to be minus 2.5 volts per microsecond. So you can see it directly from the circuit as well, and this is also important to be able to look at the circuit and gauge the answers. So it will start off with a slope. Okay, if you calculate the slope of that line, it will be minus 2.5 volt per microsecond, or minus 2.5 times 10 to the 6 volts per second. But of course, the slope won't stay that way. It will keep on continuously reducing, and asymptotically the voltage goes to 0. Okay, this is Vc of t. So one point of interest is, if you draw a tangent at t equal to 0, where does it meet the x-axis? Okay, that is the 0 volt line. This is where the voltage is 0 volts. So this is a tangent, and we know that the slope is minus 2.5 volts per microseconds. Okay, so if you calculate this time, it will be 2 microsecond, and it's exactly the same as tau. I am showing this as a numerical example, but if you use the general form of the expression Vc of 0 exponential minus t by tau, then the initial slope is minus Vc of 0 by tau. Okay. So, if you keep on continuing over that line and go down by an amount equal to Vc of 0, you will reach tau. And at t equals tau, if you look at the voltage, you will be easily able to calculate that this is phi by E, where E is the natural exponent. Okay. And in general, if you call this as 100% or unity, wherever it starts from, then you draw a tangent, it hits the 0 line at t equals tau, and you will see that it would have fallen by 63.2% over one time constant. Okay. And you can continue this. I mean, for instance, you can draw a tangent at this point, and where it will hit the 0 line will be 1 tau away from this, one time constant away from this. So, this will be 4 microseconds. Okay, because this is a 2 microsecond and it's 1 tau away from that one. And again, if you look at how much it has gone down by, if you call this as 100% now, this part will be 63.2%. Okay. So, all these are basically saying in different words that what we have here is an exponential. Okay. So, these properties are all useful to know, again not as memorizing facts, but by understanding them and calculating them for a few example cases. Okay.